we can use the DFT. We can, sorry, that's awfully sloppy even for me. We can use the DFT or FFT to recover the amplitude, phase, and frequency of sinusoidal components of x of n. So I'm going to switch over to the slides and look at a particular example, but that presents some results from an Octave program. Okay, and it's called AMP FFT, and I'll make this available actually on the website. I'll post this, so let me flip over to the slides. So this is showing an example of, I generated this sequence in Octave, and I chose to use a sequence size of 100 samples. And so you could view this as, for this particular case, you could view this as sampling a 20 hertz signal at a 100 hertz rate, and I chose to use 100 samples or 1 second's worth of data. And then I took the FFT of this sequence. Here I plotted the magnitude of the FFT versus frequency, and you can clearly see the 20 hertz component. Now, because of the nature of the discrete Fourier transform, any frequencies above the folding frequency, any frequencies above fs over 2, if x of n is real, will be reflected in frequencies fs minus our frequency. So with a frequency of 20, a sampling rate of 100, a real sinusoidal component that appears at 20 hertz would also show at 100 minus 20, or 80 hertz. So we can kind of neglect any of the components that appear above 50 hertz when we're working with real sequences, because they are directly related. This is that complex conjugate relationship I was talking about earlier. They're directly related to frequencies below the folding frequency, or below fs over 2, or below 50 hertz in this case. Now, again, the amplitude of our sinusoidal signal is directly related to the amplitude of our Fourier transform. If you remember that relationship, that we defined our amplitude sequence as the absolute value of x of k divided by n. N was 100, x of k is 400 here. Divide that by n, and we get our amplitude spectra. You know, it's just an amplitude scaled version of the absolute value of our DFT. Now, the amplitudes here would actually be 2 times this value. You remember both these components, actually, these would be exponential components that actually combine to give us this cosine component. So the amplitude of this thing is actually twice the amplitude here. If we look over at the Octave script, so the Octave script here actually sets up this sinusoid with an amplitude of 8, and then I add a phase angle in here of 33 degrees, and compute the FFT. Most of this then is just plotting the spectrum, which you saw on the slide, but then the last thing I do is actually calculate the amplitude and the phase angle from the correct component of the DFT. So when I run this, ideally this would display 8 and an angle of 33 degrees. And indeed, when I run it, I do see the plot that's included on the slide. But then if I flip over to the command window, I also see that it's correctly calculated the amplitude and the phase angle in this particular for this particular example. Let me flip back to the whiteboard to continue this for just a few more minutes. Related to the spectra that we've been talking about, would be called two-sided spectra. So remember, another way, remember our spectra is actually periodic with a period of Fs. So these frequency components that actually appear above the folding frequency, I could show as actually being at negative frequency. But again, we will have this conjugate relationship between those frequencies above the folding, between Fs over 2 and Fs, and those between 0 and Fs over 2. So in some cases, instead of seeing plots like this, which are called the two-sided spectra, instead you see what are called the one-sided spectra, where they just show the components between 0 and Fs over 2. And again, this is relying on this relationship that x of k is equal to the conjugate of x of n minus k. Okay. The one-sided spectra, and your book calls these AK bar. So the component at DC, or the k equals 0 value, is the same as our previous AK. So A0. But that's for the k equals 0 component. The other AK are actually doubled. So in the one-sided spectra, we'll be able to directly read off the amplitude of the corresponding cosine or sinusoidal waveform. So this is done for for k between 1 and n over 2. Okay. Similarly, for the phase angle spectra for the one-sided spectrum is the same as the two-sided spectra. The powers are different. The 0 component is the same as that for the two-sided spectra, but the other components are actually all multiplied by 2, so that you can directly read off the power here of the sinusoidal component. So this is 2 times our pk values. Again, this would be for k equals 0, and this is for 1 less than or equal to k less than or equal to n over 2. This would be for the phase, it's for all k between 0 and n over 2. Okay. And so if you go back and if we plotted our one-sided amplitude spectrum using our previous example, sorry about the crooked axis here, in k, 1, 2, 3, 4, these would be the k values for f in hertz. Again, 0, 2.5, 5 hertz, 7.5, and 10. And then, our spectrum now would look, let's call that 1, 2, 3. Our spectra would now look like this. This is our one-sided spectra, AK bar. Now it only goes up to so these values would be twice the previous value. So this one, which was 1/2 before, would now be 1. Okay. And then our one-sided spectra would only go up to n over 2 or Fs over 2, which is 5. So this is the one-sided spectrum. I tend to use the two-sided spectra and talk about it a lot more than the one-sided spectra. And the two-sided spectra is actually a little more general. It even will give you the correct frequency components in the case where x of k is actually a complex signal. The one-sided spectra is useful only when x of k, or our time domain sequence, is actually a real sequence. And although that is very common, sometimes, particularly in communication, we will work with complex sequences. So let me wrap up this video, and we'll continue this lecture with a final video on zero padding.